Alright, hi everybody. So, hope everyone's having a good afternoon or evening or morning or wherever you are in your day. We're going to spend a few minutes talking about polynomial regression. And so this is a topic that at least I think is a little bit easier than interaction terms, which is kind of nice. So we'll get a little bit of a break from some really difficult stuff and head into just some moderately difficult stuff. And so a polynomial regression model just in general just refers to any model in which one of the explanatory variables is squared or cubed or raised to the fourth or whatever. And so some examples include just our usual linear regression model technically falls under this because it's just raising x to the first. Our quadratic regression model is just a model where we have our predictor variable squared as a second term. And our cubic regression model, as you might probably guess, is going to have the x squared term as well as an x cubed term if your data looks like it's following a somewhat cubic trend. And so polynomial regression models are still linear models, and so this is kind of an unfortunate use of terminology, I think, and that in stats a linear model just means that the model is additive in the beta coefficients. So even though x gets cubed, this still qualifies as a linear model. So pretty much everything that we have talked about and will talk about in this class is a linear model. So one example would be just having two predictors additive in these beta coefficients. That counts. A second example would technically still be that quadratic regression model. That still counts additive in those beta coefficients. A third example might be like our log transformation model. And so remember, we're statisticians, and so log just always means log, the natural log. And so that still qualifies as a linear model. Examples of nonlinear models, which you might recognize from a couple of other specialized fields, would be something like this. So see how that's kind of nonlinear in those beta coefficients? Or maybe something like this. And so one of these, I forget which one, is supposed to be like a model for like enzyme something catalyst relationships. I don't really know for sure, but from that field. So nonlinear models arise, but only rarely. Almost all major models in stats are linear. And so if we have that quadratic regression model, so remember that that's just the one where the predictor is squared, probably the most common of these polynomial regression models. We could think about whether we can interpret each of these coefficients. So a fitted intercept, we can definitely interpret that as long as 0 is within the range of our x values. So we might say when x is 0 units, we expect average y to be beta hat not units. So that's just our usual interpretation. Still works here because when x is 0, both those terms drop out. For beta hat 1 and beta hat 2, we can't really interpret either of these. And so beta hat 2, if you're familiar with calculus, which I know some of you have because you're stat majors, beta hat 2, we can't really interpret it, but it indicates the concavity direction. If you're not familiar with calculus, that's not really important, so don't really focus on that or worry about that. But we can reason out why we can't interpret either of these coefficients. So for example, for beta hat 1, our usual interpretation would be as x increases by 1 unit, we expect the average response, or the average y, to either increase or decrease by beta hat 1 units. as long as the other predictors in the model don't change. So take a second and you go ahead and pause this video to think about what's wrong with that interpretation. So what's wrong with it is really similar to what was wrong with the interaction interpretation when we had an interaction between two quantitative variables. If we increase x by 1 unit, just by definition, x squared also has to change. So it doesn't make sense to say, okay, we're going to increase x by 1 unit, but hold x squared constant. That just doesn't make any sense. So that's why we can't interpret either of those coefficients. The same logic goes for that beta hat 2 coefficient. And so in the your turn, you'll be working with some SAT data to answer some questions with a polynomial model. And so one of the big takeaways from that example is you're going to end up using SAT score as the response, percent takers as the predictor, and you're going to go through that and answer and fit a model with quadratic for percent takers, and then you're going to fit a model that has a second categorical predictor. And so you're going to compare those two models in the exercise, and the takeaway is that you could use two different models to answer the same question. Neither model is necessarily right, neither is wrong, but you'll see that they will both be able to fix a linearity assumption that is violated on its own. So that will be what you'll kind of work on next in the RStudio section. As always, let me know if you have any questions. I'm happy to answer anything, and we will pick up with this nested f-test next time. So have a good morning, evening, afternoon, and we'll chat soon.